Okay, so let me just, let's start by, I'd like to recap how we concluded on Friday. Using Neimark's dilation theorem for a POVM measurement, the state after measurement conditioned or post-selected on outcome K here, let me just call it K naught. Is given by okay, so some of the students confirmed for me on Friday afternoon that indeed they could not also see how to reduce this to the usual formula, but I'll get to that in a second. Okay. Where EK is equal to a sum over J MKJ, and the dagger goes probably here. Yes, that's right. Dagger goes there. Okay, so it's important to realize that let's define, so here's a series of remarks. Okay, so remark 1, define some map lambda k equal to lambda k acting on rho is equal to a sum over J sorry, there's a mistake here. This K should not be here. I define this rho K. Thank you. All right, so this is rho K prime. Actually, I don't even need the prime anymore. Prime's redundant. So rho K is the state conditioned on outcome K. In fact, this should be K naught. All right, forget the K naught. We'll just call it K. So I don't want to write knots everywhere. So I mean, I just didn't want to confuse you between here K is a general index belonging to some set, and here it's a particular outcome. I hope that's clear from context. So the particular state condition on a particular outcome K, we sum over J, and then the associated POVM element is given by this relationship between the measurement operators and the POVM element. So a POVM is a set of operators corresponding to your measurement, just like a PVM is a set of projectors. The POVM is a set of positive operators. And here, these are called measurement operators. And this is an element of the POVM. So let's define a map lambda k equal to the sum over mkj rho mkj dagger. Then lambda k is a CP map. So we can think of measurement as a kind of transformation. well, at least indirect measurement. As a kind of transformation. Where we're allowed to select a subset of systems exiting the device. So a typical transformation, every system that goes into the box comes out of the box. Here, in the case of a measurement, we have a readout on the box, which allows us to throw away systems that don't correspond to the outcome we were hoping for. You know, the outcomes are random. We can't control which outcome K we get. That's part of the randomness of quantum mechanics. So then we condition on a particular outcome, which means we throw away all systems exiting the box that didn't give us that outcome. And that's why we lose normalization. That's why this is not a CP-TP map, right? So in general, lambda K is not CP-TP because we discard systems with outcomes K prime not equal to K. Remark 2, I've probably seen the update rule for generalized measurements in about 4 different textbooks and 5 or 6 different papers. I've never seen anyone give this as the most general expression. So I'm not missing something trivial, as confirmed by the students here and students when I've taught this course previously. So here's a kind of a bonus problem. Can anyone find a reference that gives star instead of where this is star as the most general rule. It's certainly not well known, but whether it's known at all is not known to me. Well, it's known by us, I guess, now, but maybe not anyone else. Okay, so I'd appreciate that because it's worth knowing if we're moving things forward with this, or it's just rediscovering what someone figured out in the 70s already. Yeah.
Do you say lambda K is not a trace preserving map? I mean, if the post-measurement state has to be a state, you must have, the trace must be preserved.
Yeah, you can force it to be trace preserving by. So the question was, can't we always make lambda K CP-TP? And yes, we can, but then it's not lambda K anymore. We can enforce normalization by fiat. And here, by normalization, I mean renormalization of the output state by just letting rho K go to rho K prime equal to rho K divided by the trace of rho EK. Okay, so that's supposed to be a division. So what we're doing is we're taking the probability of getting outcome K. Right? So if we do this experiment 1,000 times and 200 times we get outcome K, then we can estimate that probability. But we can also predict the probability if we have a mathematical expression for the preparation, and we have a mathematical expression for the measurement, then we know the exact probability of outcome k, and we can just divide by that quantity. And then we have a description of the states that exit the device conditioned on outcome k, and we've now created a preparation procedure. All right, so then when we renormalize, we can think of the measurement device. So I told you a moment ago, we can think of measurement as a kind of transformation. We can also think of conditional measurement as a kind of state preparation. So really, the only box we need is the box. So under renormalization, we can think of measurement as a state preparation. Okay, so the only box we need is the measurement box. It's multifunctional. I guess I'm debating in my mind whether or not we have to put a little go button on top of the measurement box that wasn't there previously. But I guess the light going off is it's saying go for us. Yeah.
So if I have this freedom of reinforcing the normalization of my state, so every every generalized transformation on my state gives rise to a POVM, right?
The generalized transformation on my state gives rise to a POVM.
These are basically Krauss operators, right?
Usually the trivial ones. So if I have a CP-TP transformation, which is my normal transformation, then that corresponds to the trivial POVM, which is
the one that you can create with the Krauss operators, right?
Yeah, actually, okay, that's a good question. Let me give you another piece of information before I answer that, because you're raising an issue I'm about to mention. So point 4, the measurement operators are not unique. Are not unique. In other words, they are underdetermined by the POVM. Okay, so consider a set of measurement operators m tilde k equal to v mk, where v is a unitary operator on the Hilbert space. Okay, this means v is unitary. I guess I'm dealing with finite dimensional systems, so I'll make this some finite dimensional Hilbert space. Okay, then mk tilde dagger is equal to mk dagger v dagger. ek tilde is equal to mk dagger tilde mk tilde, which is equal to mk dagger v dagger v mk. Clearly this is identity because v is unitary. So this is just equal to ek. Yes?
In the line D belonging to U of C raised to, is that?
Oh, it's just UD, isn't it? That's the correct notation. Sorry, that was when I wrote it down, it looked funny. Yeah, so these are unitaries on a d-dimensional Hilbert space. This is the set. This is actually the group of unitary operators If you don't know what a group is, just think of it as a set. I'm not using any of the group properties here. Group of unitary operators on H equals CD. Okay, so what does this correspond to operationally, this extra V? Well, my map lambda k, let's forget about the sum over J for now and look at a special case. Lambda k then, lambda k tilde is equal to V dagger, V mk rho, this is lambda k acting on rho, mk dagger, vk dagger, which means we have, this is equal to V rho k V dagger. Okay, well, I'll be consistent and not use hats here. So we have an additional unitary action, unitary transformation arbitrary. This is true for any unit transformation as part of the state update. Okay, let me move this up so you guys can all see it. All right, now I'm prepared for your question if you still have it.
Yeah, somehow. So, I mean, you're saying here that the only function you need is the measurement box, right? But
yeah.
If I have a general transformation of my density matrix, I can write it in terms of cross operators, right? Mm-hmm. And those cross operators give rise to a POVM. Mm-hmm. So somehow I can understand that general transformation is basically choice of an outcome of a measurement on a bigger, I guess on a bigger Hilbert space or something like that, isn't it?
I mean, okay, so is the question, look, I'm saying the only box you need is the measurement box, so that means the full functionality of my transformation box should be included as a special case of this measurement operation I've just described to you. Let's say that's the question for now. Then the reason why I wanted to mention this piece is because now, what if my transformation box is just some plain old unitary transformation? How do I get that out of this? Well, I see here that my measurement operators, I can always define a set of measurement operators, take the MKs to be identity, and take V to be this freedom. Then then my measurement box has created a unitary transformation, which I'd never actually thought of before, but that's kind of a nice illustration of this claim that all you need is the measurement box. Now, this whole all you need is the measurement box, I mean, this isn't something fundamental. it was a throwaway comment, but I'm pretty sure that that's correct. That especially with this last point here, that you can even describe unitary transformations if you choose a trivial POVM like the identity POVM, and you use this freedom in the Krauss operators for the measurement to implement a unitary. I mean, I wouldn't say that this is a good way to think about quantum mechanics, but it just shows you that there's some redundancy in our way that we've divided up the problem. That was the only point I wanted to make. I mean, for now, I think it's best you think about quantum mechanics in terms of these three separate concepts. You have preparation concept, transformation concept, and measurement concept, and just keep them separate. But it's important to realize that there's some overlap in these concepts. Okay, good. Is there anything else I wanted to say? I have an example of a. I think on Friday, did I give you guys on Friday? I showed what happened to the off-diagonal elements under measurement. So the off-diagonal measurements of the density operator were destroyed. But I did not show how if you have a rank 2 measurement operator, the coherence is not destroyed. Did I show that? I suggested it I suggested it as an assignment problem, but is that going to happen, or should I just give the example in class? Okay. All right, good. Let's do that. Okay, so yeah, I'll just do it. Just want to keep it simple. I mean, I don't think in general, I feel like I should give more examples to flesh out these kind of abstract ideas. So let me do that. So this is just an example of projective measurement, of a projective measurement. So here we're looking at something much simpler than this POVM structure. We're just looking at a regular projective measurement. I should have given this example probably 3 lectures ago or something, of a projective measurement with non-rank 1 projectors. Okay. So let's take some state as our preparation. And this is a 3-level system, so a Q-trit, or a spin 1 particle. It could be a spin 1 particle. It could be the 3 most lowest lying eigenstates of an atom. Any 3-level system of interest. I guess this should be density operators to be more precise. Linear operator is correct. Density operator is more correct. Let's choose a basis. Here we're going to let rho equal psi, where psi is equal to sum over I ci phi I, where phi I, here I goes from 1 to 3, and we have the phi i's define an orthonormal basis. And our measurement is going to be our PVM is going to equal pi 1 and pi 2, where pi 1 is just phi 1, and pi 2 is equal to sum over I equals 2 to 3 phi I. Okay, so now these are both self-adjoint, obviously. So clearly, pi L is equal to pi L adjoint for both L's. And maybe I should use K here, because K is my standard measurement index. And then pi K squared is equal to pi K. So this means it's an orthogonal projection operator, which is what defines our allowed class of ideal measurements. But then the key point here is that this piece, this is a rank 2. This is a rank 2 projector. And this is a rank 1 projector. So what happens to the state under this measurement? Okay, so we perform a measurement, and we get the Lüder's von Neumann rule. Let's just call it the Lüder's rule. So Lüder's rule is that under the measurement, rho goes to rho k equal to pi k rho pi k. And then we can renormalize if we wish. I mean, I guess I'm not being consistent in, let's renormalize. All right, so it's our new state, and this is true conditioned on outcome k. Okay, so now let's do this. We have an arbitrary superposition. It's a pure state. We do this two-element PVM, one of which is a rank 2 projector. So let's look at the cases. So case 1 is going to be let k equal 1. Okay, this is trivial. Then rho goes to phi 1, phi 1. And you can see this because we have phi 1 rho phi 1 phi 1 divided by the trace of rho phi 1 phi 1, which is, this is just this. So this piece cancels with this piece, and we get phi 1 phi 1. All right, so case 2 is a little bit more interesting. Case 2 is where we let k equals 2. Then rho goes to rho 2 equal to phi 2 plus phi 3 acting on rho. Phi 2 plus phi 3, and then some normalization factor, which we're not going to calculate. And then the numerator, so here, trace of dot times rho 2. Now we write out rho, and this is going to be a bit nasty, so I'm going to do a lot of it in my head. So we have this expression. So our kets, our bra terms are going to act on rho from the left. Phi 2 is orthogonal to phi 3 and phi 1, so phi 2 just picks out the phi 2 term. But the interesting thing is that consider a term like this. So here we have the phi 2 projector, and here we have the phi 3 projector. Here, I'm going to write out rho explicitly. So rho, where can I write it? It's not, here, I'll just write recall, or note. So note, rho is equal to, can I use indices to do this intelligently? I mean, the point is I want to illustrate these cross terms, these off-diagonal terms.
Will be something like C2 star, C3,
Yes.
2, 3,
Yeah. I just don't know if I have to write all that out or if I can just write a sum and it's included in the... Yeah, I can write it as a sum. So sum over ij, ci, cij bar, phi I, phi j. There, nice. Okay, good. That's what I was hoping for. Okay, good. So now we have this compact expression for rho, which includes the off-diagonal terms are terms where I is not equal to j. And the important thing is that this rank 2 projector is going to allow some of the off-diagonal terms to survive, right? So if I have a term of the form phi 2, phi 3, this phi 2 acts on this and gives 1, so that term survives. this phi 3 acts on the phi 3 here and gives 1 by orthogonality. So that survives. So we're going to have some off-diagonal terms survive, some don't. If we have a term of the form C1, C3, which has phi 1, phi 3 here, there's no phi 1 on this side. Phi 2 and phi 3 are both orthogonal to phi 1, so that term gets killed. It gets set to 0. Even though it survives on this side, it gets killed on this side, and likewise. So what you get then is you get an expression of the form C2 squared, phi 2, plus C3 squared, phi 3, plus C2, C3 bar, phi 2, phi 3, plus C3, C2 bar, phi 3, phi 2. And the important point is that these two terms, these off-diagonal terms, correspond to coherences. Coherences that are preserved by this measurement. Okay, so the way to say this, the mathematical way to say this very concisely, is that we have a two-dimensional subspace that is preserved by this measurement. And now remember, I was telling you the two-dimensional subspace spanned by phi 2 and phi 3 is preserved by this measurement. And remember we talked about how we can think of decoherence as a measurement where you don't record the outcomes, right? So the idea of decoherence is that it's an interaction instead of between an apparatus with a pointer and your system of interest. It's some other quantum system and your system of interest, but there's no pointer, so you can't read out what outcome you got, because that other system now, instead of being an apparatus, is like an environment, some unknown degrees of freedom. And so we can use the same formal, the von Neumann indirect measurement model is a model of decoherence when you do not condition, when we drop this assumption, the conditioning assumption, and instead we don't condition. Then we can talk about the state we get after measurement. So recall, if we do not condition on the outcome, then under the measurement, rho goes to rho prime, which is equal to the trace of rho pi 1 times phi 1, plus the trace. Oh, I didn't renormalize. Yeah, thank you. Yeah, right. No, hold on.
We have from the Lüder's group, without the probabilities.
We want the probabilities, though. We want them. This is right. This is right. But why is it right?
Okay, yeah.
You're right. I guess the renormalization we did, it's like an ad hoc step. Plus trace of rho pi 2 against, let's call it rho 2. Okay, let's just define this state I just wrote out. Oh, I already called it rho 2. Ha. But then I have to get rid of this thing. Rho 2 is actually this divided by that. Ugh. All right, it's ugly, but it's the way it is. So this one is no, we want the probability. What am I doing wrong here? Rho 2. Yeah, that's good. That's exactly what I want. But then, I don't want this one then. How have I defined? Okay, this is easy. Why am I not seeing it?
Remember that if you take the sum over all the row case times their probabilities, the probabilities cancel each other.
But I mean, the point is my state after measurement is going to have the coefficients. It's going to have.
Yeah, but it comes from the fact that if you take the phi 1, phi
Oh, I see. Oh, I see. Right. Okay, this is fine. Okay, good. It just looked weird because this is, I don't break the symmetry, but this breaks the symmetry. Okay, that is fine. Didn't look right, but it's fine. Okay, so this is our state after measurement without conditioning. And what's not obvious from this, because the notation was poorly chosen, is that rho 2 has coherences between subspaces 2 and 3. Probably should have called this rho B instead of rho 2, but okay. So rho 2 contains coherences between 2 and 3, expressed in these terms. But the coherences between 1, subspace of projector 1, and the orthogonal complement, that's destroyed. So what we've lost the cross terms, we've lost the off-diagonal terms. C1, C3, C1, C2, C2, C1, and C3, C1. Okay, so these terms, with the terms with those coefficients in our original state have been destroyed. They've been set to 0. So this is a model of a decohering environment which preserves a two-level subspace. So this is this idea here is essential to things like quantum error correction. This idea is critical to quantum error correction. Just called QEC. So remember that quantum error correction is a fundamental idea in quantum information that even in the presence of noise, it's possible to introduce techniques that allow you to preserve the information in a way that's robust against that noise. And so one of the techniques in quantum error correction is to say, look, this phenomena arose, think of von Neumann's indirect measurement model. This transformation here, going from rho to rho prime, came because our system coupled to a, instead of apparatus, let's use the word ancilla, so some other degree of freedom. Our system coupled to an ancilla via some interaction, and then we ignored the ancilla. So we decohered our system. The idea is that it's possible for that coupling between the system and the environment to have certain symmetries. And if that coupling has certain symmetries, then what we can do is we can move the information into a subspace that's not affected by the interaction. So if you understand something about your noise, you can take advantage of that to put the quantum. So suppose I only have a qubit, a two-level system of information. What I can do is I can move it into the 2-3 manifold, the 2-3 subspace, let the noise happen, and then that information is preserved. In general, you have much more complicated structures which enable this, based depending on the nature of the noise. So you can have, like you can have 3 qubits, which is an 8-dimensional Hilbert space, and if all the qubits are subjected to the same collective rotation, then you can find a 2-level subspace within that 8-dimensional Hilbert space, which is unaffected by that noise. And then what you do is the encoding step is to take your information on a single qubit, spread it out amongst the 3 qubits in such a way that it's actually only living in this 2-level subspace. Then when the noise happens, that subspace is preserved. So we preserve the quantum nature of the information, which is the coherences between these two levels. It's exactly the existence of these terms which gives us an advantage, these coherence terms, and protect it against the noise. So that's just one model of error correction. There are other models of error correction which work even when the noise has no such symmetries. So this is typically a model of, this is in particular a model of what's called passive error correction, or they call it decoherence-free subspaces. Decoherence-free subspaces. Okay, I'm glad I did this example, actually. All right, good. Are there any questions about that? No? All right, I'm sure if you take the quantum information course, you'll see a lot more about this. Yeah?
How general is the noise? Like, because it seems like you can do this if you know exactly what your noise is going to be, like what your noise operation is going to be.
Yeah, this passive technique, right.
But if you have, like, I mean, in general, you know that your noise is going to be a rotation in this filter space. Like, do you know the exact form of your noise?
So that's a very important question. So the question was, this, for example, assumes that you knew something about your noise, so you knew where to put the quantum information to hide it. In general, how do you know that? How do you know what the noise is? So that's a very important problem. And in fact, this is an active research area to find ways to measure and characterize the noise model so that you can design the correct error correction scheme which can deal with that noise. So there's even some controversy about the point is when people prove, there's something called the fault-tolerant threshold theorem. Does threshold have two H's? Threshold? Threshold theorem. So Dan Gottesman, who works here, is one of the people that pioneered this field. The original pioneers were Peter Shor, Calderbank, Steen, Ray LaFlamme, who's the director of IQC, Manny Nill, and others, who kind of realized that this was possible and started trying to characterize conditions under which this could be possible. So the idea is that you know, if the noise model satisfies certain hopefully reasonable so if you talk to a quantum information theorist, they'll just say reasonable. I add hopefully just because I try and be general. So we hope that this is reasonable. If the noise model satisfies certain hopefully reasonable assumptions, or conditions, I should say. Doesn't matter what we think. What matters is what the case is. If the noise satisfies certain reasonable conditions, then with sufficient overhead, by overhead I mean extra qubits, an arbitrarily long, robust quantum computation is possible. Okay? So this is a very fundamental thing that makes quantum computing a reasonable possibility to aim for. And here really the crucial assumption is this, that we have the noise satisfies reasonable conditions. And so there's two parts of that. One is that the noise satisfies reasonable conditions, And 2 is that you have a way to assess that the noise satisfies those reasonable conditions. And so this is something that I've actually worked on extensively, which is this idea of how can you efficiently, preferably efficiently, it doesn't have to be efficient, but efficiently means suppose you have n qubits, all right? So you have n qubits, you want to do some quantum computation with your n qubits. The Hilbert space dimension is 2 to the n. So the dimension of the Hilbert space is exponential in the number of qubits. This is not responsible for quantum speedup, because that's also true of classical probability theory. If you have an n binary outcome event that's random, the set of probability distributions is in a Hilbert space of dimension 2 to the n. So, but anyway, so the point is you have this exponential that appears. In fact, so then the question is, characterizing what's happening on that big of a Hilbert space, what is the dimension of the unit? Suppose your noise is a unitary operator. What's the dimension of that unitary operator? Well, it's a d by d. It's a 2 to the n by 2 to the n dimensional operator. So if I want to characterize my noise, does that mean I have to characterize 2 to the n real coefficients or complex coefficients, right? So that's a hard problem. All of a sudden, the whole point of having n qubits is that I have some classical problem like factoring, in which I have an n-bit string, and the question is, can I find the factors in an amount of time that grows polynomially with n? And so classically, there is no known method for doing that, but quantumly, using Shor's algorithm, we can do a computation which requires only n qubits and poly n operations on those n qubits that produces the factors for us. That's assuming no noise. So the whole advantage of the quantum computer is that you can do algorithms which grow only polynomially with the number of qubits. But if the problem of characterizing your device is exponentially hard, that's kind of a problem, right? So if I want to do Shor's algorithm in polynomial time, but I have to do an exponential time experiment to characterize my noise in order to find the right error correction scheme in order to implement Shor's algorithm, then I haven't really gotten an exponential speedup, have I? Now you could say, well, look, it's a one-time cost. I do this one time with this particular device. I spend exponential resources characterizing the device, making sure it satisfies the reasonable conditions I need for fault-tolerant quantum computation. And then I can do then you can start just pumping out numbers as long as the number, and then I can, for each such number, I can find the factors in polynomial time. So it's an unfortunate exponential, which you can kind of say, well, it's a one-time cost. Every time I do the algorithm for a different choice of input, it's only polynomial. But what would be ideal is to remove that exponential cost altogether of characterizing your noise model. And so this is something I've been working on for a very long time, about 10 years now. And one of the schemes I propose is called randomized benchmarking, where you perform a random circuit, essentially, that has to satisfy certain properties. And by looking at the output of that circuit, averaging over random realizations of circuits, you can get a reliable estimate of the error rate and indeed other features of the noise which are relevant to choosing the right error model. But that story is not complete. So that's a partial solution to the problem, but it only works for what's called the Clifford group, which is a subgroup of the unitary group, which is not universal. And what I'm working on right now are ways to generalize that scheme for a universal gate set. And actually, yeah, so while I've got my head in the clouds half the time about quantum foundations, this is the kind of the practical research I do at IQC. It's one of the things I do, I should say, which is work with experimentalists for them to find ways to characterize their devices, preferably efficiently, so that they can find out, well, one, are they doing what they hoped? How well are they doing? And of course, the long-term goal is to completely characterize the noise model to demonstrate that it meets the conditions for some fault-tolerant error correction scheme. So if that's something that's interesting to you, you can come talk to me about it, because I'm always looking for students to work on that. There's some very beautiful mathematics that goes into that, some group theory and representation theory. And so the mathematics in and of itself is very interesting and very rich. And it just turns out that the same mathematics is relevant to coming up with toy theories that demonstrate all kinds of quantum phenomena, even though they have a perfectly classical epistemic meaning. Okay. Was that an adequate answer? Okay, good. So yeah. Okay, good. So then with the last little while, what I'd like to do is answer a deep question. Some of you will hopefully go on to string theory and quantum gravity, and I think it's useful to be able to understand something about the mathematical structure of quantum mechanics and how it relates to the mathematical structure of classical mechanics. And this is not very well known. It's actually originally due to Dirac, and with some work by other people kind of filling in the holes. Okay, so let's remember classical mechanics. So we have Hamilton's equations of motion. Which I'll write down for fun. dq by dt is equal to p over m, and dp by dt is equal to minus dv by dq, where we assume we have some Hamiltonian of the form p squared over 2m plus v of q. And then we have quantum mechanics. And quantum mechanics is the von Neumann equation. Okay, so this says that my time evolution for my density is equal to, I actually looked up the signs for you guys. That's how much I care. Oh, sorry, let me write this as a commutator. So it's rho h in that order divided by IH bar plus rho by dt. Is that right? Minus sign. No, I mean, sorry. Does this term even exist? This term is just in the Heisenberg picture, isn't it? Yeah, this is 0. Sorry. That's 0. And I should make this a partial because there's no other, well, it's the only dependent, so I guess it doesn't matter. Rho is only parameterized by time, so let's make it a full differential. Okay, so the commutator is equal to rho h minus h rho over IH bar. Oh, and then of course this is true. This is true if this holds for pure states. Rho equals psi psi, in which case it's equivalent. Is equivalent. In fact, it's better than equivalent, but I don't know how to say that precisely. It's equivalent. It's equivalent to Schrödinger equation, except it removes the gauge freedom of the overall phase. Schrödinger's equation. Okay, so equivalent is the wrong word. Schrödinger's equation has this overall global phase because you're dealing with vectors, and the overall global phase is not physical. So strictly speaking, when you deal with Schrödinger's equation directly, you should talk about the equivalence class of vectors which differ only by a global phase. Okay, so this is it, and then we have classical mechanics with incomplete knowledge. Which is always the case. And then you have the Liouville equation, which is d rho by dt is equal to d rho by dt equal to dh by dp d rho by dq minus dh by dq d rho by dp. Is that the right order? It might be minus and plus. Okay, that's one sign I did not look up for you guys. It's easy to figure out, so we could just figure it out. df by dq, yeah, so that's plus and minus. So there.
Okay, so you're assuming a closed system.
Yeah, closed system evolution. We're back to closed systems. Okay, where rho is, so here clearly rho hat is a density operator on the Hilbert space, and here rho is a probability distribution, so it's an element of L1 on some phase space. Okay, and T parameterizes how rho varies in time. Okay, so the question is, can we come up with a mathematical framework which includes these theories as special cases? And so the answer is yes. Run out of board. Sucks. All right, let's work over here. All right, so here's Dirac's idea. Where is my... Okay. Okay, we define the Poisson bracket. So Poisson bracket is defined by the following conditions. A, anti-symmetry. Anti-symmetry. So here F and G are elements of some space of functions. I don't know how to prescribe exactly what that space is, but just think of them as polynomials. Are, for example, polynomials in Q and P. Okay, this is e.g. is our polynomial functions. Okay, let's just say we're dealing with polynomials. So we have variables Q and P, and we have functions that are polynomials in Q and P. So we have an antisymmetry condition, which is that the bracket between F and G is equal to negative GF. We demand linearity. And then you have some scalars, A and B. Let's allow them to be complex. And then you have AF plus BG, Poisson bracketed with h. H is another polynomial. F, G, and H is equal to A of F, H plus B of GH. The third condition we impose is Leibniz's law. Leibniz's law is essentially a product rule. So the Poisson bracket of F with G times H is equal to F Poisson bracketed with G times H plus G of the Poisson bracket of F and H. Oops, at H bar. We have the Jacobi identity. Which is that F Poisson bracketed with the Poisson bracket of G and H plus H Poisson bracketed with the Poisson bracket of F and G plus G Poisson bracketed with the Poisson bracket of H and F is equal to 0. And the last assumption is that we impose a value for the Poisson bracket of our fundamental quantities Q and P. So we demand that Qi Pj Poisson bracket is equal to delta Ij, and that Qi Qj Poisson bracket is equal to 0, and Pi Pj Poisson bracket is equal to 0. So this is for I not equal to j, of course. Oh no, this is for all I and j actually. Okay, so who knows their Lie bracket by heart? So some subset of these correspond to a Lie bracket. I think 3 of them, maybe 4, maybe the first 4, or maybe just 3 of the first 4 are the rules for a Lie bracket.
I mean, C doesn't apply necessarily.
So A, B, and D are Lie bracket.
Yes.
Okay, so yeah, so the Poisson bracket is a Lie bracket with extra structure. In particular, this product rule, and in particular that we have a preferred set of variables that satisfy this. So this is a formal bracket, which then if I give you any 2 polynomials, and I say, what's their Poisson bracket, you can evaluate them by just breaking it down. So if I have a third order polynomial, I mean, ultimately I want to get it down to just a Q or a P, so I can directly apply this rule. But suppose I have some term in a polynomial which is P squared Q. How do I break that down? Well, I use the product rule. This is P squared Q. Let G equal P squared and let H equal Q. Then I can evaluate the Poisson bracket of something with that. Here, I bring out the Q and I bring out the P squared, and I reduce the polynomial degree of the arguments using Leibniz's law. So in this way, I can evaluate any polynomial via the Poisson bracket. So now what Dirac realized, and this is so amazing, what he realizes is, hey, look, so what Dirac said is suppose that my primitive variables P and Q, which these are actually vectors. I'll forget the vector symbol. It should be clear. Say Pi and Qj. Suppose that they form a commutative algebra. Okay, so then what that means is in particular that if I have P times Q, that's equal to Q times P. Okay, for every I and J. Suppose that's the case. And now I don't know the right way to do this, but you could probably couch this in operational terms. And I never really thought that through very carefully, but you could think about it as something about, I mean, maybe this could be made an operational statement by thinking of it as the commutativity of measurements or observables or something like that, but I'm not sure. Anyways, you suppose that's the case. It's just a mathematical assumption of commutativity of these algebra elements. Then what you find and this is a mathematical fact which I cannot prove to you, but I believe it's true because Dirac said so. Then there exists, no, actually, I'm sorry. We can verify directly that it's true. Scratch that statement. Then there exists a representation of the Poisson bracket of two functions f and g as df by dq sum over I dg by dpi minus df by dqi, df by dpi dg by dqi. Yeah.
So at this stage, where you say F, G, and H are falling within Q and P, are you assuming anything about Q and P, so do they commute at that point? Or are you just saying that there's some
That's not.
Q and P are just elements of
Q and P are just elements of some algebra.
so they might not be commutative.
These aren't. No. We're assuming nothing about commutativity here. So the assumption of commutativity starts there.
Okay, so Q and P are anything, F and G are falling.
Yeah. So suppose that Q and P are commutative. In fact, we can identify. Let me add another sum here. Sum over alpha. Here, alpha belongs to, say, x, y, and z. So we can make each of these alpha. Okay, and then we can think of, so for one, there exists this, and then statement two. So statement two is that we can think of qi alpha as equal to xi, yi, and zi. So the idea is that these are the spatial coordinates in 3D. In three-dimensional space. And then similarly for the momenta. So we actually interpret these physically as the coordinates of three-dimensional space and the momenta in three-dimensional space. Pj alpha, Pj beta, Pj beta. Okay, so this is for particle. Sorry, I completely blew this. Let me just erase this. Here, alpha goes from x, y, and z. So what I mean is right. So based on alpha being x, y, and z, which I wrote here, we just realized that qi alpha pj beta is equal to delta ij delta alpha beta. What we're doing here is this bracket is 1 only if it's referring to the same particle. So the position of particle 1 and the momentum of particle 1, the Poisson bracket is 1, but the position of particle 1 and the momentum of particle 2 their Poisson bracket is 0. All right, so we're picking out the canonical pairs that basically the momentum of particle 1 has a special relationship to the position of particle 1, but it doesn't have a special relationship to any other degrees of freedom. The bracket's 0.
You're talking about canonical variables. You have an algebra of P and Qs, right? In an abstract way, without referring to classical mechanics, how can I determine if both are canonical conjugate to each other? Because here I can...
over here, how do I do this here? This is
Symplectic form.
Not
but so somehow
that
this
is
is
how
what we
you
want.
determine that.
But I mean, you define canonical conjugate variables.
Yeah, you have to define that.
So this is for one particle, so I just put this all here. Okay, so here the Q's and P's are just, this is just a list of coordinates, so Q is equal to, Q1x, Q1y, Q1z, Q2x, Q2y, and so on for P and Q. And then I impose this, which is the same as that, actually. And then the other thing I wanted to do is say, prior to making that assumption, so right there I said, suppose we have a commutative algebra. Let's forget about that. Before we make that assumption, let's assume we have a fundamental dynamical law. For some polynomial function, we assume the following: df by dt, the time evolution of that polynomial is prescribed in terms of some Hamiltonian, Poisson bracketed with the function, plus if that polynomial has any explicit time dependence. So if the coefficients of my polynomial have an explicit time dependence, then that shows up here. But if my polynomial is a polynomial in Q and P with constant coefficients, then this term is 0. Okay, this is for explicit time dependence in the coefficients. In coefficients of the polynomial. This entire structure I'm showing you is true for a larger class of functions than polynomials, I'm sure, but I've never gone through the exercise of determining that set. So we assume a fundamental dynamical law, and we define the Poisson bracket as a fundamental bracket that has these properties in terms of our primitives, our primitive algebra elements, or I guess they're generators of the algebra. And then we say, okay, now suppose that these variables commute. Then it turns out that there exists a representation of the Poisson bracket in terms of a differential operator, a partial differential operator. So when I say there exists a representation, and I said I didn't know how to prove that, that was not true. I know how to prove it. All you do, take this object, make sure it satisfies all 5 postulates of the Poisson bracket, and then you confirm that this is indeed a representation. Okay, so I can either, if I have 2 polynomials f and g, I can either evaluate the polynomial, the Poisson bracket of them, using this recipe, this very formal recipe, or I can evaluate the Poisson bracket just by plugging the polynomials into the right-hand side here, and I'll get the same answer both ways.
Is this a unique representation?
It is not unique. It is not known to be unique. That's the part that's not known.
So then the question is the one that is unique, the unique one that makes sense in classical mechanics. I mean, that reproduces Hamilton's equations of motion, that stuff.
Well, this is going to give us Hamilton's equations of motion. But we don't know if it's unique. So if you assume you have a commutative algebra, there may be other representations. I don't know the answer to that, and it's arguably, I would suspect it's not known, is what I mean.
Yeah. Okay.
What?
I just was worried about that any representation that I have to choose for this have to make physical sense, but no sense in classical mechanics.
I mean, I think this is, if I was a PhD student, I would study this in my spare time. But I'm not. So, I mean, there's some, you know, the mathematics of representation theory is something I know a bit about, but it's a very deep subject that I don't know as well as I would love to know. But if someone is good or interested in representation theory, I think that's interesting. Because, you know, if you're interested in theory building and understanding how to unify quantum mechanics and gravity, things like that, this, for me, would be an interesting thing to explore, to my mind. OK, so the point is you make these two assumptions. We take assumptions 1 and 2, combined with this framework, this abstract framework. And then what we get is this implies classical Liouville mechanics. And I think it also, in fact, it probably almost certainly it implies Hamilton's equations of motion, which we can just take as the limit where our knowledge goes to certainty and it becomes a Dirac delta function. Okay, that's what I have in mind. Hamilton's equations of motion. But in particular, what we do is we identify the function f as just our phase space density. And then you can prove that d rho by dt is equal to 0. Okay, this is proven in Goldstein's classical mechanics, like chapter 11 or 13 or something. I'm not going to reproduce it. I always get confused between partial and full-time derivatives when you're dealing with some fluid dynamical flow in a phase space, but that's how you have to think about this. And keep track of those things correctly. You can prove this. And this, in turn, implies that d rho by dt is equal to this Poisson bracket of rho with h. Okay? So this assumption, assumption 1 was needed. In fact, I think that assumption 2 here is equivalent to assumption E there. So this was redundant. No, I don't think so. Well, supposedly it's not because I looked it up and checked. I mean, you have to be really careful with this because remember that we're going from the full to the partial. So you get an equation like that. Oh, right. Yeah. Minus signs. This needs a minus. All right, good. All right, so see, this is why I don't look up minus signs. I'm going to get it wrong anyways. There. Here, we'll just change the order. All right, H rho. There, thank you. I apologize for that. Okay, so now we get to the upshot. Now here's what's really cool. I assume Big Brother will yell at me if they can't see this on the video. I don't know that I. Oh, here we. Yes. So now the next assumption. Now instead, so here, this is case A. Case A. Now case B, here's case B. Case B is this. You say now assume Q and P are not commutative. Qi alpha and Pi alpha are not commutative. Okay, this is a mathematical statement. It'd be really interesting to articulate this as an operational rule. But I don't know how to do that. Then you can prove that there exists a unique representation. We can show, and this is easy, it's about 4 lines, which I probably won't do for you, but you can do it yourselves. We can show that there exists a unique representation of the Poisson bracket as a commutator. We can only prove it's unique up to a proportionality. Okay, which means that then we make as an ansatz, we assume the proportionality is IH bar. I'm sorry?
Isn't that fixed by the fact that the bracket between canonical variables is 1? And you, by other means, show that Q and P have commutator IH bar.
What, you mean this statement or this statement?
I mean, the answers of the proportionality.
The ansatz, that the proportionality is IH bar? It's 1 over IH bar, yeah, well, yeah.
I mean, it is an answer, or you can fix it by knowing that the canonical variables will have a Poisson bracket 1, and you can show by other means that the commutator is IH bar.
Well, you need, I think H bar is an experimental constant. So that tells you right there you're not going to derive this mathematically. I mean, maybe you could deduce that it has to be complex, but I've never seen anyone do that. But definitely H bar is, what, 6.34 times 10 to the minus 34 or something like that, right? It's an experimental number. So, I mean, maybe you can derive it from some deeper theory, which would be amazing, of course. But for now, I mean, I think we just have to accept it as an ansatz. Okay, so the amazing thing is that this is a unique representation of the Poisson bracket up to a proportionality constant. And then we get the von Neumann equation. So this implies the von Neumann equation. Where we now notice that what we do is we add hats, right? We add hats here. What do the hats mean? Not yet. They don't mean operators yet. It means non-commutative. It's a reminder of non-commutativity. They're operators, and you realize that non-commutative operators via the Stone-von Neumann theorem admit a representation as linear operators on a Hilbert space. Okay, so we get quantum mechanics in L2R or quantum mechanics on a finite dimensional complex space. That all comes from that. But so here we have the hat. The hat means non-commutative. Hat means non-commutative. And then we get the von Neumann equation, which is that d rho by dt is equal to 1 over IH bar of the commutator of rho with H and we assign where we identify rho as the state. Rho is, it started out as some polynomial and ended up being satisfying this rule. And then later on, then via the Stone-von Neumann theorem, there exists a non-unique representation of Q and P hat as linear self-adjoint operators on L2R. Okay, so that's how we get quantum mechanics. So it's amazing to me that we could have an abstract formulation which includes quantum mechanics and classical mechanics as special cases with their very different structures via just this assumption of commutativity versus non-commutativity. Yeah?
Somehow, by doing this, you're saying that I can take a quantum phenomena, right, reproduce it in this abstract theory, and kind of taken a classical analog, right?
They're both
Because I have a lot of
the same
problems with
structure.
that.
That's not the route I would normally go.
Okay.
That's not, I mean, this really is a very formal mathematical abstraction of the structure of the theories. If I wanted to look at analogs, I would just say, well, what theory do you get out when you look at this? Well, you get Liouville's equation, Hamilton's equations being a special case of complete knowledge. So, you have this mathematical structure, which gives rise to, 300 years of celestial mechanics. And here we have this structure, which gives rise to, 90 years of describing the atomic world.
So you have some canonical coordinates or whatever that are non-commutative, right?
Mm-hmm.
So you're somehow saying that this coordinates span a quantum phase space or something like that.
I mean, I can make those kinds of
I mean,
statements.
I looked at the analogy of very well, but there's something that, for example, spin and all of that I cannot. I mean, I cannot derive from a general theory as this.
No, I mean, oh, sorry. I actually misspoke earlier. When I said, Stone von Neumann gives you quantum mechanics in L2R, we actually don't get finite dimensional quantum mechanics from this.
Okay. And
So we don't get spin half, and I misspoke when I said that. So this just gives us wave mechanics without spin, and then we need other structure. So I mean, I don't feel like this is a complete story. I feel like this is a very insightful story, which I mean, you guys are supposed to be the next generation of scientists that are going to teach us things we didn't know. So this is I think a piece of a puzzle, and the puzzle is not complete. That's how I'm presenting it. Yeah, so basically I'm telling you guys all the things that, I wish I could work on. Just, here's a nice problem. So yeah, that's something to think about. And we should probably wrap up there. Okay, great. Well, I'll see you tomorrow.